Hello everyone, I'm Zhixin and come from the University of Kassel. Today my topic is uncertainty and utility sampling with per-clustering. Deep learning has a strong learning ability to process high-dimensional data and extract features automatically, while deep learning is often very greedy for data. Active learning is concerned with reducing annotation costs effectively and ensure a predetermined level of accuracy. However, a major challenge in active learning is its lack of scalability to high-dimensional data. Therefore, an approach that combines deep learning and active learning will significantly expand their application potential. Deep active learning mainly contains two parts: the ALQ strategy on the unlabeled dataset and the deep learning model training on labeled dataset. Choosing a suitable selection strategy is very critical. The uncertainty-based approach is one of the most common pole-based methods in the application because it is simple in form and has low computational complexity. Many deep active learning methods use the uncertainty sampling strategy directly. However, there are still two challenges that we have to overcome. First one, unreliable uncertainty at the initial AL phase. Second, uncertainty sampling lacks exploration. And I will explain it in the following slides. For the first challenge, at the initial stage, uninformative instances are usually selected based on unreliable uncertainty due to an unclear sense of the data space. To address the first challenge, it is critical to find the most representative instance from the large unlabeled dataset at the initial active learning phase. The general method is to use random selection at the beginning at the training process for exploration. However, this method could fail for imbalanced dataset because the selected instances are less representative, and most of them are located at dense areas. It will increase annotation cost. As another solution, unsupervised learning algorithm can analyze large amount of unlabeled data. For example, the K-means algorithm is one of the most common clustering algorithms for knowledge discovery in data mining. The clustered information is helpful for active learning in two aspects. First one, the instances located in the center of cluster are more representative than the others and should be labeled firstly. Second one, samples in the same cluster are likely to have the same label. For the second challenge, uncertainty sampling utilizes batch acquisition and queue the top n instance with the highest score. However, it is likely to select a set of information-rich but similar instances. It leads to insufficient exploration. A feasible solution is to use a hybrid queue strategy to enhance the exploration of uncertainty sampling. The similarity between samples is a method to measure the similarity among instances by clustering the feature vectors distance between each other. But in the opposite direction, we can also utilize the similarity to filter similar instances out. In other words, after sorting a batch of instances based on uncertainty sampling, we could filter out a similar instance to improve the exploration of selection structure. So in this case, we propose our algorithm uncertainty and utility sampling with per-clustering. For short, we say it UUPC. The two core ideas of our proposed algorithm are: first one, at the initial phase, we label the instance close to the cloud center to train the model for estimating reliable uncertainty. Second one, the selection of the most informative instance depends on two strategies: uncertainty and utility. The uncertainty evaluates the probability of Bayesian neural network to an instance. The utility filters out the instances which are similar to the already labeled instance. Since uncertainty sampling lacks exploration in the data space, the utility metrics help the model discover some more valuable instance but far away from the current decision boundary. Compared to the baselines, our algorithm can achieve a higher classification accuracy and fewer annotations. Selecting the most representative instance from the unlabeled data by labeling cluster centers is heavily dependent on the quality of clustering result. In k-means, the crucial parameter that affects the goodness of clustering result is the number of clusters. The more clusters, the better the clustering result, but it will increase the cost of labeling. So the number of clusters should be optimized. So in our approach, there are 4 unsupervised evaluation scores are involved. The optimized cluster number is located at the minimal space. Then we only label the instance close to each cluster centers and put them into the label set and to train the neural network. At AL phase, we propose uncertain utility selection strategies. We use Bayesian neural network to estimate the probability. The theta are simple t terms and get a Monte Carlo estimate of the prediction probability distribution on the label y as the average regarding a new unlabeled instance x star. In our case, we calculate the entropy over the predicted class probabilities of a new instance to estimate the uncertainty score. The uncertainty metric requires to be enhanced with an exploration of the data space. Although in the initial stage, we use per-clustering to help Bayesian neural network to obtain reliable uncertainty estimations quickly. Some valuable instances are still far away from current existing decision boundary. Therefore, we define a utility metric to enhance the exploration of uncertainty sampling continuously. The standard deviation of the similarity between the instance and each class represents the tender of which class it belongs to. The higher standard deviation indicates the instance is likely to be classified into one single class. When the standard deviation is lower, the instance is located at the intersection of multi-class, and annotation by the oracle could be more benefit. Here is one example. X1 is located at the intersection of 2 classes that has higher utility score. X2 is more close to 1 class which has lower utility. In the end, we will combine uncertainty and utility together to select the most valuable instance. In this article, our proposed algorithm also supports batch-based training. The picture on the left side is a complete process. In summary, at the initial AL phase, we do per-clustering and label all instances which close to the cluster centers, and then we do the initial Bayesian neural network training to get reliable uncertainty estimation. At the active learning phase, for each instance in unlabeled data pool, we use Bayesian neural network to calculate uncertainty score and apply utility score to enhance the exploration of original uncertainty sampling. In each batch, we select top n instances with the highest UU score to label through Oracle and put them into labeled dataset. Okay, let us come to experiment evaluation. The first experiment is tested on a low-dimensional and small artificial dataset that could visually show the acquisition behavior of different selection strategies. For UUPC, the first selected 5 instances at AL initial phase are marked as gray squares. Uncertainty sampling only has 1 decision boundaries on the left side, which lacks exploration. UUPC initially selected instances are located in the 5 cluster centers, which represent the whole data space. Selecting the most representative instance could help the Bayesian neural network to estimate reliable uncertainty at the beginning. In this experiment, our method has the highest F1 score compared with other deep active learning strategies. For the second experiment, it aims at evaluating our method the UUPC's performance on real-world balanced and imbalanced dataset with high dimensions. The following figures illustrate the F1 score of the test set with the different amount of annotations on training set. We label 5% unlabeled instance in the unlabeled site. Uncertain sampling does even worse than random sampling when the number of annotations is smaller than 200, due to unreliable uncertain estimation at the beginning. Our method, UUPC, could keep a higher F1 score not only on balanced but imbalanced dataset, which is up to 4.5% higher than other baseline methods, until the number of the annotated sample is greater than 800. Conclusion: the direct use of uncertain sampling in deep active learning could face the following two main challenges, which I mentioned before. In this article, we propose an effective deep active learning algorithm, UUPC, which enables the model to explore the data space at the initial stage using per-clustering, and enhance the exploration of the model based on a combination of uncertainty and utility metrics. The preliminary experimental results show that our method outperforms the baseline method in balanced and imbalanced dataset, even under fewer annotations. Now let's go to future work. Currently, we only did some preliminary experiments. There are some works needed to do in the future. First one, in the current preliminary experiment, we only apply a tiny 3-layer lineage network and flatten the image data without considering image features. We could extract features through CNN from high-dimensional data in the future experiment. Second one, according to our test, K-means algorithm works slow on high-dimensional data. We could use autoencoder to reduce the dimensionality of data before feeding to K-means. Third one, we only do preliminary experiment on artificial and mini's dataset. We should test on more dataset and compare with other DL algorithms. Last one, UUPC and other mentioned methods might fail in anomaly detection scenario. One potential solution is performing isolation forest or DB scan at the initial stage of active learning to get the rough decision boundary and then refine the result through our uncertainty utility score selection strategies. Then, thank you so much for your attention.